12, a mamy naprawdę mało czasu. Dobra. Hello everybody. It's my pleasure to meet you on this talk, JVM in the Age of AI, where we'll be talking about, as you probably can imagine, AI. And I'm very happy that you all gathered there. Okay, you said there won't be no problem, and there are problems, like always with Max and presentation. However, it will probably getting better as we speak, because I thought that in 2024 everybody is already expert in AI. Because it's probably something everybody is interested in, everybody had opinion about, and I was worried that I won't add much to the discussion. However, I found a bit different perspective, and I hope you will like it. Small introduction to me, very short because I do not have much time. I'm Artur Skowroński. I'm the head of Java Kotlin development in Virtus Lab company. If you have heard about us, you probably have heard about because we are the Scala steward, so we are responsible for the Scala language development. Who is using Scala? Wonderful, because I do not use Scala as well. So, okay, so we are on the common ground. I can make jokes about Scala and feel comfortable with that. Wonderful. And what I would like to talk about today is AI. However, AI is a very broad topic. Broad to the level that everybody is defining the term a bit differently. So let's start with creating our common ground. Okay, why the slides are not, why you are doing that for me presentation? However, maybe go this way. What we'll be not talking about today. We won't be talking about the LLM through API, because, you know, it's not that very interesting, especially if you are Java engineers. We are just doing some AI call. They are very interesting topic connected to that, not for the JDD. We won't be talking about the data engineering, totally different stuff, and probably different conference as well. Model development, the same story. However, what I would like to talk about is the usage and inference from existing models in the Java and JVM languages, and mainly about the GPU programming. However, if I had told you that in the abstract, probably you wouldn't be there. So AI, I promise it will be still interesting. Okay, and also one important disclaimer, it will be helicopter view. Every topic I covered, I'm covering from the bird's eye. So if you want to go into further details, I'm very happy to provide so. However, we have just not that much time because we have 45 minutes and 139 slides. I gotta go fast. So one thing, don't turn your back, don't look away, and don't blink. Always wanted to use that Doctor Who reference. Okay. So we are now starting, as you see. Okay, I have already 20 slides behind me, so it's not that bad. A bit of theory. Because what the model inference is, like I said, it's 2024. Probably everybody have heard about it on some time in the past. So just quick introduction. Whenever we are training our model, we are talking about taking a huge amount of data, looking for the common patterns in that, and doing some mathematical stuff to create the set of parameters that will define relationship in those data. And that's model training, something that is out of the scope of this presentation. However, we'll be talking about the inference process. So taking that already pre-trained model, present it to the new data, and doing some kind of the prediction. Because what machine learning models do, they are doing prediction. And inference, in theory, looks like that each model have multiple layers. And on each layer, we need to do a lot of computation. We are doing the calculation, mostly matrix calculation. The bigger the model, the more the calculation. And after all those mathematical, very easy in truth, mathematical computation, I will be describing how easy in the later part of the presentation, we are receiving prediction. And prediction can be the next token, it can be text classification of email classification or image, so generating a layer of image, generating something. Like I said, prediction. That's why we cannot trust our AI models, because they are doing the best work they can, or sometimes messy one. So this is part about the inference. Mostly inference in practice are done through the framework like TensorFlow. Who have heard about the TensorFlow? So, like in the practice, everybody is currently the machine learning researcher, because what programmers do nowadays, like I mentioned. And however, TensorFlow is not the only project that is used for the model inference and working with the machine learning models. There are Keras, there are scikit-learn, there is PyTorch. Each of those has a different model format, approaching topic from a different perspective. However, they have one thing in common. They are using different models, they have a different approach, they have something in common. All of those are using Python. That's why Python became the most popular thing in the world. So the first approach, which we, as a JVM developers, and now we are getting to the JVM part finally, we should probably, as there is already existing ecosystem of tools and frameworks, maybe we could just reuse it. And ladies and gentlemen, GraalVM is coming. Who have heard about the GraalVM? Okay, also a lot of people. And probably what you have heard about the GraalVM when you heard about the GraalVM is the tool that allows you to build faster, smaller, linear application as a native image. However, that's just the half of the truth. Because original paper, and yeah, we are getting to the paper part of that presentation, was called One VM to Rule Them All. And the goal of the project was to create, apart of being the wonderful Lord of the Ring reference, the goal of the project was to create the, like was mentioned, one VM to rule them all. And to explain what it is, let's focus on the JVM first. Java Virtual Machine is the virtual machine, no, it is the platform that allows us to run multiple languages. Apart of Java, we can run Kotlin, we can run Scala, we can run Groovy, and you can treat all of those as a syntax sugar over the JVM. I know that Scala people do not like when I call the language syntax sugar. However, it is what it is. It just works that way. So the goal of the GraalVM is to create the virtual machine that will allow you virtually everything. So you can run here statically typed languages, dynamic languages. You can also currently, through the project like Sulong, you are able to also run the C code. So just the common platform for everything. We do not have time to explain how they achieve that. I have totally separate presentation for that. I was presenting it during this year GeekCon. It's a very interesting topic. However, what is interesting for us, here is yet another paper, so self-optimizing AST interpreter. Because apart of doing the JVM, it's a virtual machine itself, they're also creating something called Truffle. And Truffle is the result of that paper. It's the last paper during today's presentation, I promise that. Oh my God, why you are not changing the slides? It sometimes happens on Macs, hate that on Macs. Okay, just turn it off, turn it on, it's working. And what the Truffle is? Because Truffle is interesting piece of technology. It allows us to create, us as a developer, JVM developers, to create language interpreters that can be run on the JVM. What does it mean in practice? In practice, that means we are able to create implementation of the Python interpreter, JavaScript interpreter, Ruby interpreter, Java interpreter, that's a very interesting one, distribute it as the jar, and just have include as a dependency of our project. In practice, it looks like that. So this is real example of using the Python code in Java. We are having the GraalPy resource, GraalPy, so Python Truffle version of Python. We are having eval, any JavaScript developer here, because eval was a thing in the JavaScript community. And now we are able to just get, just pass as a string piece of Python code, evaluate it, and get the result. So, wonderful, case is closed. We can just run Python in Java, and it's working. It's working very well. However, there's always however. There are some problems, because most of the times, whenever we are talking, people are doing Python, they are doing C++ with Python syntax sugar. Because most of the machine learning libraries, all the computation that is happening is not done in Python. Python is too slow. It's done in C++. And Python is used for running those libraries with some easy-to-use interface. And here comes the problem. Here comes the problem because once again my slide blocked. However, we probably will just use the common trick all the time. The problem is that while the GraalPy is very good for running the Python code, it's not that easy when we have that native part. Currently, the native extension, so running the Python, that C code run through the Python, it's possible. Still, oh my God, I hate it when it happens. Still, and this is something what happened here, it seems that most of it needs to be recompiled, it needs to be distributed, you need to have it just, compiled by the JVM, distributed, available for our application. So for each of the projects that is included to our own system, it needs to be done. And JVM team is doing great job here because, like you see, there's TensorFlow, there is Keras, there is PyTorch. There are many other projects since the beginning of year because since March it's possible to do that. However, still, and I hate my presentation, will do. Compatibility is not great yet. Because while most of the biggest project is available, there's huge chance that some less known dependencies won't be accessible. So it's always working by the pure chance. We are not sure that it will be just, okay, we'll be able to run our application because the packages could be not available. We would need to, each time there's new package, you need to recompile it and distribute as binary. It's a mess. It's a mess, and even people from GraalPy are agreeing that it's a mess. So that's probably the shortcut doesn't exist. So if shortcut doesn't exist, let's go the true hardcore way. Let's do the inference of models from Java itself. And like I mentioned, all those Python dependencies are just frameworks. And if they are frameworks, we can re-implement them in Java. And that's what we are doing. We have TensorFlow for Java, we have Tribuo, that is a framework from Oracle, we have DeepNet, also some different projects like Deep Java Library from Amazon, Deep Learning for J. All of those can be used. However, the problem is that each of those projects, it's just its own thing. They have different API, different approach to the problem, different vendor, different recycle. So we do not have standards. And everybody probably have seen that XKCD comics in the past, but this is a twist. In Java, it worked pretty well for the history of the language. We are pretty good in creating standards. Because we have JPA, we have JDBC, we have JAX-RS, we have Server API, we have a lot of different standards that are, and for which we have different implementation. It's done through the JSR, Java Specification Request process. Here you can see the bigger list, and one of the JSRs available is Visual Recognition VSREC API. And this is closest to what we have as the machine learning standard for Java. Once again, however, there is one problem with this. Let's just take a look. Okay, we have two implementation reference, one and another one from the Amazon. So it's not that it's just the singular JSR and no implementation. Still, there is one problem. This problem with my presentation once again. I don't know why Keynote is doing that for me and just for the projectors. However, just look on the list of examples. We have the linear regression, logistic regression, flower classification, handwritten digital recognition. It's not something people expect from the machine learning standard in 2024. Probably we should expect generating image, generating text, because that's what AI means in most projects in 2024. So the truth is that, nobody cares. So this is the project that has no traction at all. And this is just one problem. The other problem is that while we are good at creating standard for the machine learning space is very, very hard. There are projects, like we mentioned, each of the projects has its own model format, and they are having that for a reason. Even as there are some standardization effort like ONNX, unfortunately, each of those has its pros and cons, and when we are doing some common layer, we are losing those, we are going just to the common version. And for Java, for the creation of the machine learning models, the most important thing is performance. because we are doing huge amount of the computation, huge amount of the data provisioning. So having the common architecture is not always the best approach. We have two kinds of complexity whenever we are talking about the model inference. The first one is computational complexity. So we need on each layer and bigger model, bigger layers that probably the good mental model. We need to do a lot of matrix multiplication on each of the layer. So this is one problem we have. The other one, the model size of the models is with many layers is very, very big. They have a lot of parameters. They had millions of those, and storing them is one thing. Providing them to the application is the other problem. So we have two problems: computation and memory. And there are hard problems. However, great guys in the JDK community try to solve those. And the first optimization that I will be providing you today, it's half floats coming from the project Valhalla. Who have heard about the project Valhalla? Also, a lot of people. Great. This is the project that's goal is to make memory, Java memory layout great again. And one of the efforts for that is introducing new data types. One of those is so-called float 16. To explain what float 16 is, let's first focus on what standard float, otherwise called the float 32, is. In standard floating point numbers, commonly in our floats, we have 32 bits, which some are allocated to sign numbered, 1 bit. 8 bits are created for range, so what is the biggest and the smallest possible number in our float, and also some for mantissa, so precision, between 1 and 2, how many numbers you can scram. For 16 bits, half floats, 16-bit ones, there is a different approach. The different approach in practice means that we have they have just 16 bits, so 1 bit is for sign, 5 bits is for exponent, so we can have smaller numbers, and the range is smaller, and also between 1 and 2 we have just less possible numbers. However, this is optimization that is quite fine for machine learning models because they do not need to be that precise. So this is something that will just get us a bit of the memory. However, love it. And Valhalla is currently working on that thing. This is the screenshot that I did 21 September of 2024, so a month ago. And there was in the 4 open pull requests, 3 were connected to the project to the half floats in project Valhalla repo. Currently, it's just 1 because other ones were integrated into main repo. So they are just doing that right now. Still, half floats giving us a bit of available memory. They are not the silver bullet because size of memory is not the biggest problem. The biggest problem is the speed in which we can provide our model with data, because we are just moving data to the registry, to the CPU, to the GPU. The transfer of speed of transferring the memory from one piece of the part application to the other is the most important thing. So now we are getting to yet another part of the presentation because we will need to start talking about the native calls. And first thing, because we are to make, because we need to be sincere. We are joking that Python programmers rely on the C++. We are doing exactly the same. JVM is written in C++, and while JVM itself is very, very quick, very, very up to speed, currently for the most things that needs to be most efficient, we still use C++. And deep learning for J was one of the inference libraries I was presenting to you. And getting to the memory part, you will see that underlying C++ code is used using the GNI. About the GNI will be in a moment, to make the process as quick as possible. And also, there is used something called the ND arrays. What are the ND arrays? We will be describing a bit later. Let's first focus on the JNI. Who have been using JNI in the past? Maybe is using it right now. How do you like the process? Who likes using JNI? Okay, we have one hand tentative, so great to hear that. JNI stands for the Java Native Interface, a framework that allows Java code running in the Java virtual machine to interact with native applications and libraries written in other programming languages than C and C++. For years, that was exactly the approach that we used to just connect with the outer world outside the Java virtual machine. It was created in 1997 in Java 1.1, and the MacBooks looks like that. You know what? They looked pretty decent. I expect something worse when I was looking for the picture. However, legacy is the dated standard. That's why Project Panama was introduced. And Project Panama, like the Project Valhalla, is working with the memory layout. Project Panama goal is to work with the foreign access. So foreign access to the memory and foreign access to the programs and libraries written in C. So it has multiple parts. The first one is the foreign function memory API, probably the most well-known one. There are the others. The one that will be probably the most interesting for us today is Vector API. And before we go to the Vector API, it's time to the first time in that presentation, a part of the introduction, talk about the GPU. However, briefly, because, you know, most of the application in the real world, machine learning application, works on the GPU. That's the reason why, that's the reason why NVIDIA stock grow to the moon. That is, however, there are quite interesting stories about that as well, maybe for the lunch session or something like that. However, NVIDIA just become the best, one of the the biggest winner of the whole ML craze. However, probably most of the currently available machines and servers, they are running, our machines, they are running on the CPU. And CPU is more powerful than the GPU in our machine. So let's discuss the topic, how we can, if TensorFlows and other frameworks are GPU optimized, can we have models that will be optimized for, way of running models that will be optimized for running on the CPU. And as an example, how one of those models, we can use Llama 3, who have heard about the Llama 3. Okay, also a lot of people. It's probably the most popular open source model, open weight model. However, the difference is not that big and not that important here. Model that was distributed for Facebook and currently probably the standard for the models that everybody can tinker with. And if you can tinker with something, tinkerers will come. And one of the first approaches, maybe we can write the framework that will allow us to run Llama models on the CPU. And there is a project like that. The project is called Llama CPP. And this is this is Llama C, Llama CPP. There are two of those, probably not that important detail. Llama CPP is 700-line C++ based inference implementation optimized for the CPU inference. It's just the 700th line of the code. Because the truth is, this whole machine learning stuff, so inference, is very, very easy. It's just a lot different multiplication of the matrices. It was possible to be implementing the 700 lines of the C++ code, and currently, if you are using Llama or any other project, probably you are just having the Llama CPP as the inference implementation. Still, like I mentioned, it's very easy. You're just going layer by layer. You can implement it by hand, and then run in your application. So, if it's possible to write such a program, people will write it. And the first, also in Java. And the first approach for the problem is to create the Java bindings for Llama CPP. So just using JNI, creating options to run those CPP program in the Java world through the connection through the JNI. So this was one of the first approach. However, probably the less interesting one, because we are just having the layer over the CPP. The more interesting one, and I probably should just click more often, and because that seems to work well, it's Llama 3. And Llama 3.java, it was created by Alfonso Peterson from the GraalVM team, so the people who are doing the most crazy stuff in the JVM space. And this is the Java implementation of the Llama CPP. He just decided, I have the free weekend, and this is truly how it happens. He had the free weekend, and decide, okay, there is CPP code. I will try to rewrite it in Java. And that's how Llama 3.java happened. It's around 2,000 lines right now, so a bit more than C++, however, still a file that you can just include in your project and read those models. It's running blazing fast, because it's running on the JVM machine, and we can just simply use it on the CPU. Blazing fast in comparison to the other CPU-based frameworks, because there are limitations of the hardware that cannot be surpassed. Oh my god, what is... Okay. Okay, it's getting better. It's getting better. Are we getting there? This is the first time that happened during the presentation. Okay. And my time is... I don't know if the reason was that my corporate account wanted me to just provide the password. However, well, just give me a second. We are here. We are back here. So it should be available in the second. It looks like Mac just decided to restart. It was funny. Okay. We are getting there. It never happened for me in the mid of the presentation. You need to have it needs to be have first time all the time. Okay, just give me once again a second. You should never trust Macs. They are not reliable at all. Okay, we are back. We are back. It was quick. I'm happy it was that quick. So once again, Llama 3 Java. However, it's not the only project that is doing similar stuff. There's also the JLlama, so a bit more feature-complete implementation of the LLM inference engine. That is also including the different kinds of models, because you have Gemma-Him, you have GPT-2, you have BERT, so much more full-fledged. It was created by Jake Luciani from Cassandra team. He is currently fully into that. Okay. I'm fighting with my own presentation. Okay. I hope it worked on your side as well. Okay, so he was bragging that it's running even faster than C. So whenever somebody talks to you that Java is slow, it is not. Okay. And all those projects needed to have yet another component that is currently being introduced. Because to make Java that fast, you need to do a bit of trick. The trick is called SIMD. And by SIMD, I mean that it's the single instruction multiple data computation. And to introduce single input multiple data, I need first start with single input single data. This is some standard model in which CPU works. So we have multiple pieces of data, and we have some kind of instruction. Whenever we are working on some kind of data, on some piece of data, we need to rerun instruction flow. The SIMD, in practice, single input, multiple data, is batching it. If we have the single instruction, we have multiple piece data working on the single instruction, we can just rerun that instruction of all those pieces of data in the less cycles of the CPU using the quicker access to the memory. That just brings a lot of speed. However, that's also important caveat that JIT compiler is already doing that for us. Whenever we have loop in our code, in trying to do so-called auto-vectorization. If you heard about the auto-vectorization, it's just rewriting our code in the way that it's using the SIMD instruction because they are quite popular in the CPUs. However, JIT is doing its own thing. We do not have control over it until now, because currently we have something called Vector API. It is in the 8 incubator. So it's still preview, just passed by each of the version of Java. JDD, we are just having it in the incubator. The reason for that is it's waiting for Valhalla to be delivered. So I want to see, I was on 20 incubators, something like that. That will be fun. That will be very, very fun. Still, it's such a powerful API and such important right now that it's used in the production code. So we have the incubator feature that is used by JLlama, is used by JVector database, and many other projects, because it's very powerful and allow us to do the whole inference of something programmers want to do in 2024 very quickly. And we had also, we covered the model size and memory complexity. Now let's, once again, it was computational. What we covered here is computational complexity. However, that were just, I would say, some kind of the direction we do not want to go into production. Because in production, mostly whenever we are going with machine learning models, we are using the special hardware. And when I mean special hardware, I do not mean that special hardware, because I learned doing the research for that presentation, there were the CPU made specifically for Java. It was created by Azul and is discontinued right now. However, we have special Java optimized CPUs in the past. I'm talking about the GPUs. And GPUs had time of its life when they was the crypto, and probably nobody expected that it will happen once again in the short period of time. Apart of the GPU, we are also having the TPU, so special tensor processing units made specifically for the machine learning calculation. We also have FPGA, so the programmable gateways, the hardware that can just, we can just optimize for the very specific task, so making it uber efficient. However, all those expect us to use a bit different approach to programming. So there, once again, it will be overly simplified example. It's not how the GPU works in the practice. However, I need to introduce some topics. It's a simplification, however, something that should just give you a picture. Whenever we are doing the calculation on the CPU, even if we have our SIMD instruction, so the one that is batching our data, we still have just a handful of threads. And each thread is able to run through the single instruction. We can make them parallel, however, you have a limit of our parallelization. It's how CPU works. In GPU, the process is quite similar. However, we have a lot of cores, because GPUs were made for the graphic computation, so each pixels needed to be re-rendered 60 times a second. And each pixel is recalculated by itself. Once again, simplification. So we need a lot of cores that are able to handle that. A lot, all the time. So they are using the special model. The model is called ND-Grid. You already have seen that name in our presentation, and kernels. In those, a lot of models. What is the problem with having a lot of different cores? It's very hard to provide them with data, because we can do parallelization. However, how this parallelization could be executed, we will be just passing the piece by piece. No, it don't work that way. To have it extremely efficient, the CUDA, so the most popular model of the the most popular model of the GPU programming delivered by NVIDIA, they introduced something that is called ND-Grid. And ND-Grid refers to a multidimensional grid of threads used for parallel computation on GPU. And because it can just do calculation 2D, 3D, like necessary in games. The GPU runs threads in grids with multiple dimensions, allowing kernel to practice in different dimensions. So what I already mentioned. So ND-Grid is the data structure that will allow us to just pack itself with data. You can pack it with data. The data itself is called kernel. And the kernel is a piece of code that is executed by hundreds or thousands of threads simultaneously. Each thread runs the same code, but operates on different data. So this way we can achieve the huge amount of parallelization, because we are just passing a lot of data to the GPU, and GPU then decide how to execute it. This is the model that is used for the GPU programming, like I said, the most popular one. And in Java, of course, we have been doing that for years, because we have projects like JQuda. JQuda is using the JNI. So JNI comes back. And what is the problem with JQuda on JOpenCL is the fact you're probably not able to see that clear. However, this is the string. So the code for the kernel needs to be provided as a string, not something that is comfortable to be used, not something that people would like to have in their production. However, JQuda is probably what currently is the, I would say, the basis of the whole Java machine learning ecosystem in Java. They are just embedded. So However, like we can agree that this is not the best solution. So for years, there were different approaches how to include define the kernels, so those pieces of data in Java. And in the past, there was Aparapi and Rodbeer projects, and they wanted to introduce the structures as you see in the code, this is just the kernel object that have the run method, and you can provide the kernel code here. This way, it will be translated to the GPU code and be executed. However, what they do not provide, they do not provide any grid code and also some other stuff, because they do not have the lack of support for the proper data types. You just need to use the primitive ones, not something very efficient and not something we want to do in practice. Lack of support for diverse hardware. Each of the projects were delivering code just for the single hardware. So there was, Aparapi was from the CUDA, and Rodbeer was for the OpenCL, so AMD. OpenCL, so something delivered by the AMD. Probably also something that not giving us a lot of compatibility, and also the code that they were creating was pretty inefficient. And to get a speed, you needed to do manual hacks. So nice start, nice try, nice first approach. Probably it worth to go a bit different path. And the different path came in the project Sumatra, because parallel processing. What comes to your mind when you see parallel processing? Okay, I will help you. Streams parallel. This is something that is in the JDK since JDK 8, and they got clever idea. Maybe we can make stream parallel to run on the available hardware. If there is something that can be done on the GPU, let's do that on the GPU. Because we already have common structures for exactly that. So this was a nice idea, and GraalVM, once again, hero of our story, is coming back. They wanted to reuse GraalVM to generate the proper code. Unfortunately, and the code GraalVM could, as it has a compiler, it could just create code for the CUDA and for the OpenCL. Unfortunately, it once again was a flop, because data transfer between JVM and the GPU was so slow that the whole computational benefit was lost. It was just too slow. And mostly the project was mostly based on the GraalVM, just reusing GraalVM, so not many things were added, just running the part of the parallel code on the GraalVM. They decided, okay, maybe that's not the good direction. GraalVM itself, it's something very nice idea. However, we should go a bit different direction and get back to the drawing board. So Project Sumatra, it was never killed. However, it's currently can be considered dead. So before we go to our final hero coming from the OpenJDK, let's focus on the project that reignited the blast, reignited the spark of the GPU programming for the JVM machine, the Java Virtual Machine, TornadoVM. And TornadoVM, okay, learning for the previous lesson, it wanted to be, because it's existing project and very good one, to be full-fledged solution. They introduced the 3 important APIs. The first one is the task API that can be translated to kernel. So we have some particular task. It can be used also as the annotation. So as the most of the code is made through the loops, we can just make the loop annotated with parallel, and it will be transferred to the task. However, they probably very ingenious implementation was task graph. So something like in Gradle, when you can create dependency between tasks. So we are able, as a developers, provide the dependencies between different kernels, how they will be interacting with each other, and saying, okay, now it's your turn. Optimize it for us. And that's what TornadoVM is doing. It's using Graph Optimizer, something similar to the Query Optimizer in the relational databases, that is trying to decide what is the best way to run our code, because it's no dependencies between particular parts. Then that execution plan is just provided to the execution engine. And execution engine decide on which hardware is best to use the particular piece. Because if we can do something in parallel, probably GPU is a good choice. If it's not possible to parallelize, maybe the CPU will be the best. And then each piece, each task, is compiled to the proper environment. It can be using GraalVM, because GraalVM, the fork of the GraalVM, because GraalVM is very good for any kind of the compilation, as we already mentioned. We are able to run Python as the jar dependency to our project. And it's resolved with CUDA, OpenCL, PTX, or any other hardware-specific format. TornadoVM provides, like I said, task graph is the direct abstraction for ND-grid, so we can create that ND-grid using our task graph. It has access to the different backends, so we can run the same application on a different hardware, something that wasn't possible in the previous approaches, because we needed to pick the proper hardware before we started our implementation. It has option to manage memory, because once again, it has its own optimizers, and JIT support through GraalVM, so it's generating code in the fly. TornadoVM is a very interesting project. In my day, published their own programming model available on the Fuji. It's a very interesting document if you want to get through it. And until now, when I was presenting this presentation on Devoxx this year, it wasn't yet possible to run JLlama on it, because there were some missing parts. Last week, it was, and this is screen from today, it was to inform that Llama 2 fork is able to be run on TornadoVM. So they are it's possible right now to run the first inference process. So they are using just the standard frameworks we currently have. So this is very interesting development, and they are probably one of the challenger for for being the most important GPU framework for Java. However, they are not the only one, because there's also one approach to the topic from the OpenJDK team. And now we are getting to the nowadays, because the previous year, JVM Language Summit 2023, JVM Language Summit is the biggest event for the JVM developers, people who are doing a lot of heavy lifting into the VM itself. There was presentation, Java and GPU, are we nearly there yet? Because Oracle see that machine learning is very important use case for any piece of technology. So now, let's think how we can do that with Java in the standard way. They were approached to Sumatra was that, however, let's restart the idea. And that idea is heterogeneous accelerator toolkit called HAT. And what HAT is going to provide? It's going to provide the Endurance API. This is one thing. It's using Project Panama, so all those development of Project Panama, because it's there, as ability to provide the memory very, very fast, has access to the memory segments, things like that. So it's using the parts of the Project Panama. However, it introduced also something like code reflection through the Project Babylon. And how code reflection works, because they are a very interesting piece of technology. Code reflection is extension of Java reflection that allows access to symbolic representation of Java code, such as methods, bodies, and Lambda expression at runtime. It means that Java code knows how to rewrite itself in practice, in the runtime. This is something that can be put between the abstract syntax tree, which has a lot of details, the details that make it unmanageable to just being programmatically transferred to the Java code. It's just too complex. Bytecode itself has type flattening, so it's not specific enough. Code model, so something that is brought by the Project Babylon and code reflection, it's somewhere in between. The data structure that is specifically created to being rewritten in the runtime for the particular hardware that is currently available. In practice, it looks like we have JDK, and through the process of code reflection, we are creating our code model, and programmers are able to just create yet another piece of code that will be optimized and run on the GPU. On the fly, everything on the fly. It's something similar to because Project Babylon, for example, to give you an example, is also used for it's something similar to the link that is happening in the C# community, however, probably much wider. And they have the first success. There is a Triton language, open source GPU programming language for neural networks created for OpenAI. And they are, right now, exploring creation of the fork that will be able to run the JDK using the code reflection. It is something that is happening this year. The model is quite capable to do that. It's not production ready yet. However, like I said, we are getting there. So, wrapping up the HAT, we have Babylon that have code reflection and allow us to just create the code for the particular hardware, one important piece. so computation. We have also Panama, that is ready. It was delivered in the JDK21. So currently you can use it on the production code, and it's very good for working with off-heap memory. So something that we are able to also use for our GPU programming. So we are getting there. We are getting there, and probably it will take as much time with Valhalla, because the JVM language Summer in 2024 just bring the modest update. It's not that you can use it right now. However, in the future, maybe that's the approach that will work. Okay, conclusion, what the future holds, because I'm wrapping right now. I would like to once again go through all the projects that I mentioned. The first thing, Panama and Valhalla themed. That's very interesting story, because it's in the incubator and everybody is using that. So probably there's no option it will change, because it will be that would be the MS. I know that people were saying exactly that about the string templates. However, with Vector API, probably it's not possible to change it right now. You can use it if you need it. Valhalla half floats, they are there. However, they are waiting for Valhalla. Vector API is not waiting for Valhalla. Half types are waiting for half floats are waiting for Valhalla. So we probably need to wait a bit more. GraalPy, it's here. It's possible to run the Python libraries. They are doing a great work providing the extension, and each new version of the GraalVM is bringing more of those. However, it's pretty dangerous and not that fast yet. JCUDA, something that can be, if you are fine with writing the kernel code in string, why not? It's just working because it's the standard JNI. Sumatra, what is that might never die. This is the project that is still there, however, it's not actively developed. TornadoVM, we can say it's one of the contender, like I mentioned. It's interesting project that currently the fact is that they are going very heavily into the machine learning space, because they want to introduce, they are currently having the Paravox AI startup. It's startupish because they don't have proper products. However, they are trying to go into that direction to make TornadoVM work especially well with the model inference and model training. And also we had Hidden Babylon. If it work out, that's probably the future of the GPU and machine learning programming for Java. Machine learning inference, because that's what we have been talking about. Okay, it was quick, 150 slides. I hope everybody is still alive. Sorry for the technical difficulties. However, we get there. And if you like stuff like that and learning about what is happening on the edge of the JVM, I am the author of the JVM weekly newsletter. I like it. I heard about some people who also like it. So if you want, please subscribe. And now I don't know if we have time for the question. However, waiting for your question. Thank you very much.